Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel, Chemistry the Mystery of Molecules. Today's topic of discussion is group 1 alkanide, better to say the negative species of that alkali metal. Ne minus H plus. Yes, sodium is in negative. So we shall discuss about its preparation and its stability. So before going to details, one MCQ. What is the product of this reaction? 4 options are provided. Please pause the video and try by yourself, and definitely at the end of this discussion you will have your right answer. So now let's come to the point. What is the definition of this alkanide? It's actually a chemical compound in which the alkali metal atoms are anionic state. For example, when we say sodium chloride, we say sodium plus Cl minus, but in this case if we say this alkanite means sodium minus. Yes, I know it's unbelievable, but that's true. That's the chemistry, and that makes this thing very much interesting. Now with charge or oxidation state -1, it's true, alkali metals were known to appear in only as cation having oxidation state +1, and that's why you can conclude that these compounds are generally very much unstable and could be synthesized only under very specific condition, and they are extremely reducing agent. Why? In order to understand that, you need to look at on the periodic table. This is group 1. So here these all atoms electron configuration are ns1. So removing one electron, they achieve the nearest noble gas configuration. So that's why they all are reducing, and they prefers to get the M+1 oxidation state. Now first of all itself they are extremely reducing because they have a tendency to give one electron and convert into this M+. So electron is produced along with that, so they are actually reducing because of this produced electron. Now by special technique or reaction condition, you are converting this M+ into M-. Means what is the electronic configuration then? NS2. So it doesn't want to keep electron and it is carrying 2 electrons. So that's why electrons are very loosely bound and it is highly interested or prone to give someone that electron. That's why they are very much reducing. Not only that, they have a electron density over it, so that's why they could easily be polarizable. Generally we say the polarizability term, for example when we discuss about the anions, not only this one, anions case we say polarizable because it has negative charge, so electrons are loosely bound, so that's why they are polarizable. But in this case of this Mn minus, just consider how much loosely bound these electrons are, so that's why they are one of the most easily polarizable species. And not only that, since they have excess electron they don't want, but due to some cases they are carrying, so they are generally very big size. From atomic point of view I am saying, I am not saying group anion, it's an atom based anion. This is one of the very big size. So I guess you have understood why they are extremely reactive, because forcefully 2 electrons are given on them when itself they don't want to like to keep 1 electron. And we know in the periodic table these group 1 elements are most reducing in nature. Now so in order to prepare that, what it does, it could only be produced by special stabilization of the counter anion. What do I mean? For example, you want to prepare Na-, so there will be some X which will be plus. So first of all this is unstable, it's true. Now if the counter cation is very stable, then that is possible, because for any particular chemical reaction the condition is delta H equal to delta H minus T delta S. So if this delta G, for any reaction to happen, the condition of spontaneity is delta G must be negative. So first of all, entropy friction not interested, because we are dealing with metastable species, low temperature, so contribution of this part is less. So we need to consider about enthalpy part. So one part is extremely unstable, so another part need to be extremely stable. So that part we need to decide the cationic stability, or in this case, since they are extremely electropositive, it's very difficult to stabilize them by traditional chemistry. That's why some interesting special type of chemistry is utilized, because the stabilization of the cation is important to bear the negative charge on alkali metal anion. And in this case, alkynides represents some of the largest and more polarizable atom species due to very loosely bound electron, just I told. So question, how it could be prepared? And one of the path is cryptate. What do I mean? First of all, that cryptate means it's actually coordinating species which coordinates sodium, and this sodium cryptate species is very stable. Okay, so you can read that element of sodium and potassium dissolve very slightly in ethylamine from extremely dilute solution, but when a macrocyclic ligand like crypt222, actually please remember this is also a bicyclic. Why? Because in order to get an open chain compound you need to cut twice. I shall show the for structures after some time. So when crypt is added, the solubility increases dramatically by the factor about 10 to the power 3 to 10 to the power 4. From these you can understand how much stability this cryptate is provided to the metal, in this case sodium. By cooling such concentrated solution containing sodium below -15 degrees centigrade, an unusual golden compound sodium crypt222 is produced with an interesting properties. It is isolated. The compound is found to be actually sodium plus cryptate ligand and sodium minus. So cryptate sodium and sodide, this sodium minus is called sodide, like chlorine to chloride, sodium to sodide. One of the few known compounds contain alkalide ion, or better to say anions of alkali metals. The overall reaction actually is happening. Two sodiums are ionizing, one is sodium plus and another is sodium minus, and in this case the positive charge anion is extremely stable because of this cryptate cyclic ligand. So why it's stabilizing? If you look at the structure of this 222 cryptan, it is producing the thing. You can see here there are 2 nitrogen and in this case 6 oxygen, and we know this all the atoms have their lone pair of electron which they can donate to the central metal ion, and because of this donation, or better to say the word encapsulation, means it consumes the metal ion inside this, and after coordination you can see these blue are these nitrogen, these are nitrogen, these 2 blue part, and red are these oxygen. So these are oxygen. So all are coordinating to the central metal ion with their lone pair, means this is encapsulation, means it is actually covering the metal ion with a electron cloud. We know metals are positively charged species, means electron deficient these cations are, and you are covering that cation with electron rich species. So consequently this get huge amount of stabilization. So that's why this cryptate sodium is very stable. Consequently this complex, this sodium cryptate cationic part is so much stabilized such that the anionic part remains outside, because no additional anions are there. So that excess electron which is rejected from this sodium plus is taken by the another sodium molecule, that is sodium, and converted to minus. And by the way, there are other type of complex, this encapsulation, like this is called crown ether 15 crown 5, which is also famous for sodium plus encapsulation, but this is also not able to produce this sodium counter anion along with it in under stable condition, but this cryptate do. Why? Because if you look at this, the donor side is less, in this case 5 donor side, whereas in this case of cryptate you will see 6 oxygen, 2 nitrogen, 8. So from 5 to 8, so increasing the number of donor side increases the stability, coordination. Second thing, cryptate means it's completely covered, but in case of crown it is not completely covered. So stabilization is more in case of sodium plus interaction with this cryptan 222 ligand. That's why along with this it produces sodium minus anion. Now in this context a very famous compound is inverse sodium hydride, or H plus Na minus, and this is a very unusual situation occurs in a compound, this dubbed as inverse sodium hydride. Why inverse? Because generally we say sodium hydride means sodium plus and hydride minus. because sodium is more electropositive metal, that's why it is plus, and the electron is given to hydrogen, which takes the electron and produce hydride, and we know this hydrogen can behave as group 1 element as well as it group 7 element. It's ambiguous character depending on the counterpart. So that's why this is called inverse, since in this case the material contain hydrogen plus and sodium minus, then hydrogen should be extremely stabilized, as I told some time before. It's true. And in this is actually differs from the ordinary sodium hydride in having much higher energy content due to net displacement of 2 electron from hydrogen to sodium. What do I mean? See, generally sodium prefers to have sodium plus. In this case, sodium is carrying the electron density and trying to be sodium minus. So consequently, the overall means that this sodium, hydrogen plus sodium, and this organic moiety is having relatively more energy compared to simple sodium hydride, or you can say that sodium hydride plus 15 crown 5 if you take. So this is more stable. So this is less stable because the sodium is carrying the negative charge. So we have understood this thing. And now due to displacement of 2 electrons from hydrogen to sodium, a derivative of these inverse sodium hydrides arises the presence of the base adamanzane. What do I mean? This adamanzane is the ligand shown here. You can see this is the organic part, not including the H plus. So this is actually a nitrogen 4 compound. This, if you look at, this is actually a nitrogen 4 tertiary amines are there, 3 degree nitrogen, and we know nitrogens have lone pair and there are 3 carbon, means 3 CH2. So what happened? These 3 nitrogen have lone pair of electron here, 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 and these lone pairs of electrons are directed in a particular direction. And if you look at this, actually 3 lone pairs in the same direction. What is the problem? If we look at the inner picture little, means from based on our understanding point of view, this way, and these all are contain a pair of electron, and we know electron pair means excess electron density. So these all excess electron density in a same towards the same direction means it is a signature of instability. And we know what is electron. Electron is a cloud of negative charge, actually it's a cloud we having a negative charge. And what is orbital? A 3-dimensional place which holds the cloud. So all the negative charges are same direction. It is a unstabilization, and in between these electron, if you put a positive charge, proton, means proton do not have any electron, it has only one nucleus, means single unit positive charge, so it get a significant amount of stability because of these lone pairs. So that's why this cationic means this organic ligand containing the proton is exceptionally stable, such that consequently sodium minus is produced, means the electron density from hydride to shifted to sodium. That's why this is called inverse sodium hydride. And this molecule actually irreversibly encapsulates the H plus and shield it from interaction with the alkynyde like sodium minus. This stabilization means nitrogen, these 4 nitrogen and proton interaction is so strong that it irreversibly binds with proton, point number 1. And since its covers encapsulate the proton, so the sodium minus can't give its electron back to this H plus, because sodium is not that much comfortable to bear an additional electron which creates the negative charge, but because of this shielding it can't give. Just recall sometime before why I told that cryptand 222 can encapsulate sodium and produce sodide, whereas crown ether can't, because of proper encapsulation. In this example, encapsulation happens for the proton, and for crypt 222 encapsulation happens for the sodium plus. And this is produced by reaction of this protonated adamanzane and this carboxylic acid reaction with sodium, and ultimately it produces the final product, and this is the reference. Now in conclusion, what we have learned today, one of the strongest reducing agent and unstable species could be generated by proper design, and that is the smartness of chemist. Host guest chemistry is very important to produce unique structure like methane clathorates. Now host gas chemistry are unique because it can provide supramolecular stability it's a huge stability, which we'll discuss in some other video. You may consider it's a long ordered molecular thing having a proper orientation, and that orientation this thing provides exceptional stability, like this adamanzane. And in this case, methane clathrate is actually a gas hydride where the methane molecule is trapped inside the ice and it is stabilized. I have already discussed a dedicated lecture, you may visit. And please remember, electron density accumulation creates unstabilization. So proton provides a significant stability. Just I have given the example. So let's come to the MCQ. What is produced? Sodium hydride and BF3. What is the product? Please remember, sodium hydride generally doesn't act as nucleophile, but this is one of the very few examples where this hydride can act as a nucleophile and replaces the fluoride, and in this way it produces the 3 fluorine is replaced by 3 sodium and produces BH3. Okay, and along with that sodium fluoride. So this is the first answer. And in the second option, what, since BH3 is a 6 electron species, it is not itself that much stable, so consequently 2 BH3 molecule join together and produces B2H6, and in this case 2 hydrogens are shared by 2 proton with this banana type bond. So this is, so in this case answer, what is the product of this reaction is, in this reaction it produces both option C and option D is the right answer. So I guess you have learned a lot. So thanks for watching, and if possible please subscribe my another channel, Climate and Chemistry, where I upload global warming and climate change related videos. Thanks for watching. See you in my next video. Bye bye.